Everybody got the email that office hours be a little bit short, and then tomorrow, piazza, sorry. I'll be at Georgia Tech, trying to make Michigan look great, of course. We'll see. Okay, the clock has started. So, our big idea on Thursday of last week was the idea of that any linear operator from one finite dimensional vector space to another can be replaced with matrix operations. So we already know that if we have a finite dimensional vector space and we choose a basis for it, we can take abstract vectors and replace them with column vectors, and m tuples and n tuples. The big thing we had on Thursday was to take the notion of a linear operator, so L of x plus z is L of x plus L of z, L of alpha x is alpha L of x. And all such linear operators have a matrix representation. And all the matrix representation means is once you've moved from abstract vectors to m tuples, abstract vectors to n tuples, whatever this operator was doing, you can capture by multiplying these m tuples by this m by n matrix. And the example we worked out was differentiation of polynomials. We took the monomials as the basis and took degree less than or equal to 3 polynomials to 4 tuples and then replaced that with a matrix operation. And the magic formula for computing the matrix representation is you take the linear operator, you work on the basis elements for x, those give you vectors in y, you take those vectors and you represent them with respect to the basis in v, those give you n tuples, and those become the columns of A. So, the representation part is sometimes painful. It's solving simultaneous equations to get the coefficients. When you do the representation on an exam, they will be simple calculations. In real life, you use tools like MATLAB, etc. And then, for me, it's always nice when I can take two ideas and collapse them to one so I have fewer things to remember. I don't know how that works for you. So if you just define a matrix representation of the identity operator, you get the change of basis matrix. So that's a convenient thing to remember. So the identity operator is different than the identity matrix. The identity operator takes an abstract vector to itself. ID of x equals x, polynomial to polynomial. Now I've got bases of these polynomials. Maybe I take the monomials here, and maybe I take Bézier coefficient, Bézier polynomials over here, whatever Bézier polynomials are. Or I take Hermite polynomials, whatever Hermite polynomials are, I take a different basis, and I still reduce them to, say, 4 tuples or 6 tuples. Okay, then the matrix representation of the identity operator will give you the change of basis matrix. And because this thing is invertible, you can go backwards. This thing will be invertible too, and you go backwards, you get p bar. Okay? Those kind of work for you, that abstract nonsense, but it's important for calculations. It's the idea. Okay, then we left off with something you're probably somewhat familiar with, the notion of eigenvectors and eigenvalues, especially since you had to play with them a little bit in homework. So we take an n by n matrix, even if it has only real coefficients, the eigenvalues may be complex. And we did 0, 1, minus 1, 0 as an example and got j and minus j as the eigenvalues. And as soon as the eigenvalues are complex, if A is real, the eigenvectors are automatically complex as well. Okay, so the definitions are that you find a vector not equal to 0 such that A times that vector is just a scalar times the vector. That defines the eigenvalues, and then VI is the A corresponding eigenvector. And then eigenvectors are not unique because 2 times an eigenvector, I put a 2 here, I put a 2 here, it works just fine. So they're not unique. If you compute them in MATLAB, it will take the Euclidean norm and make it equal to 1. So it normalizes it. We'll define the Euclidean norm a little bit later. Okay? The theorem we ended on, we didn't do the proof, and we're not going to do it today either. If the eigenvalues are distinct, so no repeated eigenvalues, then automatically the eigenvectors are linearly independent. What vector space are they linear independent in? CNC. Now, if A is real and the eigenvalues are real and you can take the eigenvectors then to be real if you want. You don't have to because you could multiply all of them by J and make them complex, okay? But you don't have to. If A is real and the eigenvalues are real, you can take the eigenvectors are real and then you can replace this with Rn, R. You'll have the same answer. So, but in general, that's why we have to play with the complex field. And then it's important to note this is not if and only if. P implies Q, but Q does not necessarily imply P. And the example is the identity matrix. It has repeated eigenvalues, they're all 1, but yet I can build linearly independent eigenvectors. Okay? And I'd like you to just kind of go through the proof, okay, of how this theorem is proven. It's pasted into the notes from Thursday. It's a really nice example if you want to show P implies Q, do not Q implies not P. It's a really nice example of the contrapositive. And it's enough to do it for n equals 2. If you understand that, you'll understand for n equals whatever, just notation after that. Okay, that's my summary and I'm sticking to it. You like it? These summaries help tie things together, but probably help you studying for exams too, okay? So, good. Questions? No. Okay. Then let's get going. Definition. Two square, that's a Q. That's a U, that's an A. 2 square matrices, A and B, are similar, and that's what we're defining, if there exists an invertible matrix P such that B equals P A P inverse. Oh, why does that happen? Okay. Since P is invertible, I'm going to multiply both sides on the right by P. So this is the same thing. as B times P equals P times A. And that's the same thing. Now I can multiply by P inverse on the left, and I would get P inverse B times P is equal to A. Okay, so this is the definition, but it's the same as writing it. You often see it written as B times P equals P times A. But once you've got that, if A is similar to B, then B is similar to A, and it's the inverse of the similarity transformation. Okay, we'll see where these things come from. But here's the simple idea underlying it. If A and B are similar, then they represent the same linear operator expressed in different bases. So if we have a linear operator like differentiation, and I use my favorite bases, the monomials, because they're easy. You use your favorite bases, which are more numerically robust, like Hermite polynomials or Bezier or something. We'll get different matrices representing them, but you can transform from one to the other by the change of basis matrix. That's all that says. Okay. So my answer and your answer are related by an invertible matrix. Is the change of basis matrix. That's what that is. Okay. Now the thing we want to get at is just the following fact. If we have a matrix and we have a full set of eigenvectors, meaning the eigenvectors are linearly independent, then the matrix is similar to a diagonal matrix. It simplifies everything if the matrix is diagonal. Okay, so we can always transform the matrix and make it diagonal. So let's see why that is true, but that's the underlying fact that we're after now. So let's consider A is n by n. Okay. With coefficients and the complex numbers. And suppose we have our n eigenvalues, not necessarily distinct, but the corresponding eigenvectors V1 to Vn are linearly independent. Okay, so if they are distinct, this is automatic. If there are repeated eigenvalues, you have to check. It may be true, it may be false, okay? So only thing I need is the independence of the eigenvectors. And the way you often get it is the eigenvalues being distinct.
You mentioned something about a diagonal matrix. Is that just when you have everything zero except the diagonal and then
Yeah, we will definitely. Thanks for the question, but we will define that in just a moment. What is a diagonal matrix? Yeah. So just giving people an idea where we're going, sometimes that helps plot out the trajectory, okay? So now here's what I'm going to do. I'm going to define M by stacking up the eigenvectors as columns. So M is now n by n as well. And I'm going to define lambda is a diagonal lambda 1 to lambda n. So to be super clear, 0 everywhere except the diagonal. Okay. Okay, so let's see what happens when we do A times M. Okay, so from homework 1, we know how to multiply a matrix times a partitioned matrix into the columns. Yay! So that's A times V1, A times V2, A times Vn. So that's easy enough. And these guys are eigenvectors. Okay. So then we have lambda times V1 in the first column, lambda 2 times V2 in the next column, lambda n times Vn in the last column. Now, this is an exercise to do at home. This matrix, I want to write it in terms of M, which is the V1, V2s all stacked up, and lambda, which is all the coefficients on the diagonal. Two choices. It's M times lambda, or it's lambda times M. It's going to be one of those, okay? Which one do you think it is? Did you vote for that one? Okay, so check this at home, okay? Exercise. So simply check that each column of this matrix is given by the corresponding column here. Now, hint. Suppose you thought it was the other way around. The V's being linearly independent is going to make M invertible. So then you'd have A equals to lambda already, okay? Because I multiply by M inverse on both sides. If I had it flipped, it'd be gone. So it can't be right, okay? But, so go through and convince yourself, though, that this is how it works out. So that's exercise 1. And then exercise 2, the eigenvectors being linearly independent implies M is invertible. hint for the solution, m is invertible if m times x equals 0 if and only if x equals 0. And if you write x as, for example, alpha 1, alpha 2, alpha n, then you'll get linear combinations of the columns of m, which means you have linear combinations of these vectors, but they're linearly independent. So the coefficients are 0. Okay? So I've given you the proof orally, but write it down and just check every single line and you'll go, I get it, okay? Why is a matrix being invertible equivalent to its columns being linearly independent? Okay, so once we have this, we know then that A is equal to m lambda m inverse, and more importantly, we get it to be diagonal by m inverse A times m. So the eigenvectors linearly independent implies A is similar to a diagonal matrix. Okay, so we just take the basis to be the eigenvectors. We represent the matrix in that basis. We get a diagonal matrix. So those of you who are in ME 464, EECS 560, Aero 550, you'll use this fact to figure out what is the exponential of a matrix. Because the exponential of a diagonal matrix is easy, okay? So that gives you a lot of hints about how to do that. Then I have one more exercise, just to tie it all together. Find the matrix representation of A takes Cn to Cn when you use the basis of eigenvectors on both copies of CNC. Hint, don't call your matrix representation A. Call it something else. But it's still true that the ith column of your other thing, say it's B, is take A, apply it to the ith eigenvector, and find its representation in terms of the basis V1, V2, Vn. Okay. So take this, find the representation. You should recover lambda. Okay, so it just gives you another way to think about the similarity part. Okay, ties it all together. If you have trouble with those, let Niels know, and at the end of the recitation next week, he can just add those solutions on for you. He'd be happy to do that. It'll take him 5 minutes. Okay, questions so far? We're getting ready to move on to least squares problems, best approximation. So there's a couple of little simple matrix facts that we need, and then we're going to go for it. So, matrix facts that we need. Look up on the web if you care. Okay? It's indifferent to me. I just need you to know these facts and accept them, okay? I don't want to go through the details of them. So, here's the deal. Let me get my numbers right. Letters N by M with coefficients in some field F. For us, F equals R or C. It is true in general, okay? Doesn't matter. It could be the rational numbers, etc. Definition. The rank of A is equal to the number of linearly independent columns of A. When you're checking linear independence, what field do you use? Well, whatever the coefficients are in, okay? Use that field. If they're meromorphic functions, use the field of meromorphic function, whatever that is, okay? We don't care in this course, but it's been good. It's been a really nice field for me, okay? So here's the theorem. The rank of A equals the rank of its transpose equals the rank of A times A transpose equals the rank of A transpose times A. Whew. That's amazing, okay? So if you care, look it up. Otherwise, matrix facts, and we're going to go on and do abstract inner product spaces starting Thursday. So the rank, that's the number of linear independent columns. Now when I transpose A and look at its columns, how is that related to the rows of A? The same. Hence, from this statement, we have learned that the number of independent columns is equal to the number of independent rows. Okay? So, number independent columns equal number independent rows. So that's kind of surprising, okay? Now, if A has n rows and m columns, what's the most independent columns it can have? M. And what are the most independent rows it could have? N. So the minimum of these two numbers, upper bounds, the result. So if you only have 2 rows and 17 columns, you still cannot have 17 independent columns. You get 2, okay, because they're the same. So the rank of A is less than the minimum of the number of rows and the number of columns. Okay? All of these things follow from this statement, number of independent columns, etc. Okay? Now remember, a matrix is symmetric if it's equal to its transpose. So now transpose A times A transpose, what do you get? A times A transpose. Transpose this matrix, what do you get? Same thing, okay, so these things are automatically symmetric, okay, so A times A transpose and A transpose A are symmetric. Okay, we will learn awesome things about symmetric matrices, but you guys played with those in homework by doing some numerical stuff. What did you find out about eigenvectors of symmetric matrices? They're orthogonal, okay? We will define that word orthogonal a little bit later, but they always have you can always build a basis of your space consisting of orthogonal eigenvectors when you have a symmetric matrix. And even if they have repeated eigenvalues, we will prove it in homework that we don't care. It still can get a full linearly independent set and they're orthogonal. So these symmetric matrices, these guys are magic, okay? Because they're automatically symmetric. Cool. Okay, so let's do that least squares handout, and then we'll come back and talk about norms and minimum distance problems and stuff like that. Bingo. Okay, so not to make you feel bad, but this is a handout I used in my sophomore Signals and Systems course. So some of the PhD students in robotics, they have to take a qualifying exam. If all you know about least squares is what's on this handout, you will not pass. You will not pass your qualifying exam, okay? Many of your predecessors have tried to pass the qualifying exam by only knowing what is on this sophomore level handout, and it didn't work, okay? You had to take it again. So just a little warning, because this is so easy, and you will remember this result for the rest of your life, every one of you. But you need to know a little more to pass the qualifying exam. Okay. So the whole thing is we have data, and I think you're quite used to the idea is, well, how could I pass a line through here and minimize my approximation error? So we should at least define what is the error, in what sense are we measuring it, and then minimize that function, okay? So I've got some data there, and they're plotted out here in the blue things. So let's fit it to a line. Y equals mx plus b. So if I were to just choose numbers for m and b, then my estimate for the point would be whatever I have now for m times my data point xi times b. So this is my ith estimate based upon a choice of m and b for the ith data point. My true measurement is yi, so the error is yi minus y hat, or if you want to flip it, it doesn't matter. The magnitude is still the same. And then the total squared error is just this, summation of the errors squared over all of the data points that you have. Okay, so we can't make the error 0 for every single data point. Yep, we could do that one, but then those are really way off, right? So we've got to choose M and B to minimize the total error. So Y hat depends upon M and B, so E depends upon M and B. E total is a function of M and B. So we know from calculus, we want to find a local minima or local maxima, stationary points. We take the partial derivatives of the total error with respect to M and B. I invite you to do that. It's a messy calculation. I'm going to show you what the answer is and how you get it. Well, not really how you get it, but how you can remember it. Okay, so we have yi equals mi plus b plus really an error term over here. We're trying to minimize that error term. So just take all of our equations we have and rewrite them like this. Yi equals mb, that is xi and 1 times my unknowns m and b. Okay, xi and 1. So yi is xi1 times mb, y1, y2 is x21 times mb, yn, dot, dot. So I'm writing them in matrix form. I'm going to call all of my measurements stacked up capital Y. The matrix I get that's multiplying the unknowns is A, and I'm going to call these vector alpha. I think in the MATLAB code I called it theta. Life is hard. Okay. So this equation is overdetermined. I have 2 unknowns, but I have 1, 2, 3, 4, 5 data points. So there is no solution to this equation. I'm trying to find a solution that minimizes the approximation error in the sense of E total. Okay, so take this equation. So we have y equals a times alpha. A transpose times y equals a transpose a times alpha. If a transpose a is full rank, meaning invertible, I get alpha equals a transpose a inverse a transpose y. Oh. Okay, you see why you can never forget this equation? Multiply both sides by a transpose. This is now the same size as the number of unknowns. Okay. And so you check that that's invertible, bingo. Now remember, the rank of A transpose A is the same as the rank of A. The rank of A is the number of linearly independent columns. Now, if this is all ones, what do we need this column to be so that it's linearly independent? Almost anything, okay? Just not a multiple of this. So if this has 1 and a 2, I don't care what's in the others, it's done. It's all over, it's full rank, okay? So it's very easy to make that matrix full rank if you've taken your measurements not all at the same spot, okay? Yeah, I'm fitting a line through 1 point. Good, I love it, okay? So the fact is, this alpha minimizes the sum of squares fit, okay? We will prove that later in the course, okay? This will be a special case of something we will call the normal equations. We will do the projection theorem. We will reduce that to calculations with a set of things called the normal equations, and then we will go back to this problem and show that this is the answer to it, okay? So we will do the answer correctly, but I'm just pointing out that you don't have to memorize very much to remember this, okay? And then on your robotics PhD qualifying exam, know a little bit more, please, okay? That's all. Okay, so I've got calculations in MATLAB, so you can go through and check those, and then when you do it, hey, it looks pretty good. Now, the only thing I want to emphasize next is you don't have to only fit a line. If this is your data, you don't want to fit a line through it, you know? That seems pretty stupid. That's local here. Maybe I could do 2 lines. Well, why not just fit a quadratic? So I can put any functions here as long as my unknowns are out in front. So I make a linear combination of any functions I want, okay? That could be C0 times F0 plus C1 times F1 of x plus C2 times F2 of x. I don't care. But it cannot be sine of C1 of x. That would not be linear in C1, okay? You can't have sine of this, but you could have C1 times sine of x. That's perfectly fine. So any linear combination, you can fit to that. And then when you write it out in terms of your unknowns, you just build up the matrix. 1x, x1 squared, 1x, x2 squared, etc. A transpose A will be 3 by 3. You need 3 linearly independent columns. Our data, you can go through and do all the MATLAB calculations and check, and then you fit it and plot it, and it looks really good, okay? So that's called regression, fitting functions to data. Think you can do it? You could have done it when you were a sophomore? Yeah. Yeah, when I taught that course, I used to teach them how to build discrete time linear models from data too, least squares fitting. It was awesome. But nobody else wanted to teach that to students. I mean, can you imagine being engineers and you can't build models of stuff from data? Anyway, it bothered me, but that's what I did. Okay. So that's the handout, and you'll be using it in homework. And you'll combine it with the matrix representation of differentiation, and I'll give you some data, and I'll have you estimate the derivative of the data. Okay, so that'll be fun. Questions before we leave this, or you can go through and read it, reconstruct it, make it work with the 2 examples there? Okay. Yes, don't doubt us, Professor Grizzle. We are super duper. Okay. Well, that's fantastic, because now we can move on to normed spaces. Okay, so I'm going to define what a general norm is, and then we'll be working towards a special class of norms that come from an operation called an inner product. So, and that special type of norm will be amenable to least squares analysis. All of the special norms will look like very fancy perhaps, but just basic least squares things, and the answers will be simple matrix calculations. And it won't matter if the vectors are functions, they're matrices, they're random variables for doing estimation, like in the Kalman filter. It just won't matter, okay, when we're done and we have this all set up. In fact, for random variables, the least squares problem will be minimum variance. Remember, the variance is the mean minus x squared expected value. If you don't remember that, we'll get to it. So we're going to set up a formalism that handles all of these cases all at once. So I want to go through what is a norm, and then we'll start working towards what is an inner product and why does an inner product always give you a norm. And these are special norms. Okay, so from now on, F equals R or F equals C, XF, whoops, come on, go away. Delete. XF is a vector space. And for 90%, 95% of what we do, it's enough to take it to be the reals. I will need the complexes because when we take eigenvectors of matrices, they can be complex even when the matrix is real. But we will be able to prove for symmetric matrices you get real eigenvalues and real eigenvectors. But until we know that, we need the complex numbers. Okay? And if you rule them out and then you prove that, I mean, you can't do that, okay? You've got to allow the complexes to occur, but then you prove that they don't. So that's why. So most of our calculations and yours in real life will be over the reals. Okay, so here's the definition. A symbol, parallel lines, maps vectors into real numbers is a norm if, and remember, for definitions, this means if and only if. Okay, first thing, for every vector in X, the norm of X is non-negative, and the only vector with a zero norm is the zero vector. I don't want to write it like that. I want to write it if and only if X equals 0. Okay, so norms are never negative, they're non-negative, and the zero vector has zero norm, and if you have a vector and its norm is 0, it has to be the zero vector. It's if and only if. This property has a special name. It's called the triangle inequality. And it says for every pair of vectors in X, the norm of the sum is upper bounded by the sum of the norms. Okay. Triangle inequality. And then norms have to play nice with elements of the field. For every element of the field and for every vector, if I take the norm of the vector scaled by alpha, it's equal to the magnitude of alpha times the norm of x, where this is absolute value, whoops, it's just absolute value when alpha is a real number, and it's the magnitude when alpha is complex. Everybody remember the magnitude of a complex number? Real part squared plus imaginary part squared, square root. If not, you can review that. I might even paste something in on Thursday to review complex numbers a little bit. Okay, so let's do some examples of these norms. So 1, f equals Rn or Cn, and the vector space is the set of n tuples. Something called the 2 norm is simply I sum up the magnitude of the ith coefficient, I square it, and I take the square root. And that has a name. It's called the Euclidean norm. Yeah. R. What are those n's doing there? They magically went away, but this is true. F is the n tuples, and this is the reals or the complexes, yeah. If it were a field, that would mean n equals 1, and I just said x was 1 tuples. Not very smart from me, but yeah. Okay. So that's 1 norm. It's also called the 2 norm. This is called the p norm, so this is by definition, It's also a sum. Take the magnitudes, you raise them to the pth power, and then you take the pth root. Okay, so it's also written like this. Summation I equals 1 to n, magnitude to the pth power, root 1 over p. And this is true for any p greater than or equal to 1, but finite. I don't know what the infinite power of a component is, okay? These are just definitions. And then for p equals infinity, it's usually denoted x infinity. It's the max for I between 1 and n of the magnitude of xi. So this is called the max norm. And also the sup norm. And also infinity norm. Okay, so if you see somebody talking about the max or the sup or the infinity, it's all this guy. So if I have a finite set, the maximum exists, and then the max is equal to the sup as well. So if you put sup here, it's not wrong, it's just uncommon, that's all. Not wrong, it's just uncommon. Okay, so only one of these things is a sum of squares. I square this one, it's a sum of squares. Question? Yes?
So sorry, you can have norms on
You can have norms and?
Can you, like, you didn't specify, I think n can n be infinity?
No, n is like 17, Avogadro's number, but finite.
Okay.
Yeah.
So is there a concept of norms in dimension?
Yeah, so question, if you have an infinite tuple, can you define a norm on that? The answer is yes, but it takes more mathematics because this sum then becomes a limit. and you have to talk about what does the limit mean. So, and those are called little script L2, little script L infinity, things like little script LP spaces. And they're very special. They're Banach spaces. We'll talk about what that means later in the course. They have lots of beautiful, beautiful, beautiful properties. Okay, so if I take a vector space and I have a norm on it, this is called a norm space. Okay. So for the same set of n tuples, I can have different fields and I can have different norms here, okay? If the field is understood to be the reals, nobody writes it down. And you just write x and the norm. So it's very common. So, because notation is too heavy, nobody wants to use it. It's just that simple. Okay. Definition. For x and y in our norm space, the distance from x to y is d of x comma y, by definition equal to the norm of x minus y. If y is a measurement and x is your approximation of y, then the distance measures the approximation error, okay? So minimizing this might be interesting for lots and lots of problems. Let's just note distance from x to y here is the same as the distance from y to x. Because then they're related by -1, but -1 comes out with an absolute value sign, and so they're the same. Now, this is where it gets interesting. Distance to a set. Yes, please.
Back when we defined the norm spaces, then should have the absolute value of alpha.
Did it not?
Oh, wait, okay, I wrote it down wrong, sorry.
It's, hey. For every mistake I make, you make 0.1. So, you know, I listen because I often make little typos. Apologize. Okay. Now, this is where things start really getting interesting. So let S contained in X be a subset. The distance from X to S is by definition equal to the infimum over all points in S, distance from X to Y. Over all Y in S, distance X to Y. Okay, so for us, that's the same thing as infimum Y in S, norm of X minus Y. So problems we're going to look at is we have an X, we have a set of things we're willing to approximate it by. Straight lines, curves, minimum variance estimates of random variables because our measurements are not perfect, okay? So we're going to have elements that we're willing to approximate this thing by. This will be built upon measurements. This might be the state of our robot. Where it is in the world, what's the values of its joint positions and joint velocities, okay? So this is something physically important to us. These are things we build by observations of that are imperfect, okay? And we try to find the element of this that minimizes the approximation error. So that's a really interesting problem if you can set it up and solve it. We will be able to do it when S is a subspace and this comes from a least squares type problem. That's what we do in Rob 501. Okay. So here's X. F, who knows? We could have all of these things and then we just search over all of these possible points, y1, y2, y3, y 10 to the power 123, okay? And we try to find that element that minimizes the distance, the best approximate, okay? So if the set is super complicated, this is impossible, okay? But when this set is a subspace, it becomes really nice. Okay, so working toward best approximation problems, or also called minimum distance problems. Oops, let you write that down. Okay, calling the minimum distance problems, that makes sense because this is the distance from X to Y, but this is really the approximation error in X searching over all elements of S. So if there is an element in here that achieves the infimum, it may not be one, right? It's an infimum. The infimum always exists. We have to prove that there is one. We'd like to prove that there's only one often, because if there's two and you have an algorithm, it gets confused when it starts trying to converge to this one and they're both solutions, okay? It causes nightmares for your algorithms when they're not unique. It doesn't know which one to go to, so it just chaotically bounces around. So we'd like to prove that the infimum is a minimum and the minimum is a singleton, it's unique. And then we have either done the best approximation of X by an element of S, or we've minimized the approximation error, but it's also the distance from X to the set S. That's why it's minimum distance. Okay, so here's notation. X star, you guys will see this all the time. Arg min, Y in S, norm X minus Y. But what does that mean? Okay, first of all, it means the minimum exists. It's not an infimum, so there is something. So that's hard. You have to prove that the infimum can be replaced by a minimum. But if you're saying X star is equal to it, X star is a point, so it must be a singleton, okay? So you see this notation all the time, and it's almost always misused, okay? No one has ever proven the minimum exists, and no one has ever proven that it's unique, okay? So when you read papers, you have to be careful. So this means minimum exists is unique, and X star is the solution of that problem. The norm of X minus X star equals the infimum over Y and S norm of X minus Y, and X star is in S. Okay? That's what argmin means. So you're going to go to seminars, you see argmin. If you want to be smart, could you tell me why that minimum exists? And then your buddy 3 or 4 down the hall goes, and why it's unique while you're at it, okay? And watch it. Okay, so the good people have already thought about it and they've done it right, okay? The lazy people have not done it. Okay, so that notation is very precise. It means there's one and only one solution to the problem. And we're seeking solutions in this set here. Questions? We're good? Okay, now. So I plot norm of X here and norm of X squared here. Everybody agree it goes like this? So when I have a one-to-one monotonic relationship, if I minimize the X squared subject to being in a set, it's the same thing as if I minimize X subject to being in the set, right? Okay? Okay, so. X star equals arg min Y and S norm X minus Y if and only if X star equals arg min Y and S of X minus Y squared. Okay, you make this one the smallest it can be, then this will be the smallest it can be, subject to lying in S. Because if you can make this one smaller, then you can make that one smaller too, okay? So, why is this of interest to us? You get it written down. If we go back to this one, it removes the square root, and it's much simpler to just look at the sum of the squares. And that gives you the least squares problem that we talked about, sum of squares, okay? So we're minimizing the square of the 2 norm. We're good? Okay, let's do a couple more examples of norms. Okay, just so we can use these. So let's let A and B be real numbers, so they're finite. A strictly less than B. And let our interval be the bounded set. Okay. So they're real numbers, they're not in the extended real numbers, so they can't be infinity. And then I want A less than B, so this is non-empty, closed interval. I'm going to let x equal to the set of all functions from a to b such that f is continuous. Why have I put it in quotes? Because we have not defined what a continuous function is. We'll do that a little bit later, but I'm going to use your intuition that a function is continuous if I can draw it without lifting my pen from the paper. Okay? Now, in MATLAB, a step function is drawn like this, right? Is that a function? If this is really it, then I've got an interval at this point and it's not a function. So the function would be here, circle, jump, and then goes, okay? So that's not continuous. So I'm going to put a bunch of norms on this. I'm going to let the field be the real numbers, okay? So the 2 norm of a function is by definition equal to integral a to b f of tau squared d tau square root. When the function is continuous, you can prove the Riemann integral exists and is finite. If a function is continuous, its square is continuous, so this number is finite, and then I'm taking the square root. And I forgot my equal signs here. Okay, so there's a 2 norm on functions. I square this, I get rid of the square root, so I can do least squares problems in functions. The p norm for the record is integral a to b f of tau to power p d tau pth root 1 less than p less than infinity. And then the infinity norm is equal to this. It's the sup t between a and b absolute value f of t. And fact. We will prove this, but not until like 2 weeks before the term is over. Continuous functions on closed bounded sets, the supremum always exists. Okay, so they have a max. So we'll prove this when we do real analysis. So it's the max t between a and b absolute value. But we will not be able to prove it until way late in the term. So this is called the sup norm, the max norm, and the infinity norm, just like when we had an n tuple. Question?
We jump from the tau t.
No. No. It's a dummy variable. Yeah, got to put x in there. I'm saving x for vectors. Let A be an n by m matrix, then norm of A equals the trace of A transpose A square root. Okay, so I can take my vectors as matrices. I take the trace of A transpose A, that gives me the sum of the squares of the diagonal elements. So sum of the squares of all the elements of A, and I take the square root, and that's another norm as well. So there's tons of them, tons of them, tons of them. Okay. Questions? We're happy? Bored? Excited? You guys are neither hot nor cold, right? That's how you like your porridge, just medium? We're almost done. Okay, so this is our goal. make sense of this picture. Okay, so the hard thing is, first of all, making sense of anything that Grizzle draws, okay? This is M equals a subspace. Okay. This is X equals vector space. Here's a point X. Let's suppose that's the vector in it. I want to approximate X by something in M. Is it this one? Is it this one? You guys want me to do this one, right? And you want it to be orthogonal. Okay. So you guys want it to be this one. You want that to be a right angle, and you want that to be X star equals arg min norm X minus Y, Y an element of M. Okay? Okay, I want that to be true. So what I need to do is, if I'm not in R2, what does this symbol mean? So if my vector space is functions, what do I mean by orthogonal? If my vector space is n by m matrices, what do I mean by orthogonal? If my vector space are random variables, what do I mean by orthogonal? Okay, all of these things, if I can give you a tool for working with orthogonality in general vector spaces, then we just formulate all of these minimum distance problems into finding an approximate such that the error vector is orthogonal to the approximation space. And that will lead to something called the normal equations, and we will get the equivalent of A transpose A inverse times A transpose Y. In all of those, we get the equivalent of that matrix formula. Isn't that amazing if we can do that? So that's what we're going to do. And instead of getting started on it, we're going to just stop now. We got a minute and a half. We'll define what is an inner product space. We'll start that on Thursday. But the whole goal is to make precise, if I have two vectors, what does it mean that they are orthogonal? And those vectors are matrices, functions, whatever, okay? Thank you. Thank you for giving me a little pep.